Dear students, I am Rajiv Kumar, Assistant Professor in the Department of Electrical Engineering in Asansol Engineering College. Hope you all are doing well with your health and studies during this pandemic and lockdown period. Till now, whatever I have discussed with you all through Google Classroom, I will start explaining all those topics serially through this YouTube platform. So I request all of you to follow my video lectures sincerely. I request you to go through my PDF notes which is already provided to you after listening to each session. We will be also having interaction session for doubt clearing on Zoom platform. You can place your doubts in comment box or in Google Classroom. I will start the session with unit 5, that is transformer. Hope you will enjoy the video and learn the topic sincerely.
Okay, dear students, in last class we learned about single phase transformer, and the topics we covered was definition of transformer, working principle of transformer. We have also derived the EMF equation of transformer, and also we solved a related numerical. So today we will proceed. Okay, so today's topic to be covered are different types of transformer. Then we will see different types of cooling methods of transformer. Then different parts of transformer and their function, concept of ideal transformer, and characteristics of ideal transformer. So let us start one by one. Okay. Number one, types of transformer. On the basis of construction, there are two types of transformer. First is core type construction and second one is cell type constructions. So as you can see from the figure itself that in core type construction, you see that the windings are placed on both the limbs, both the side limbs of this core. Okay. And one more thing is important to note that uh, both the high voltage as well as low voltage windings are placed on the each limb. Okay, so see here, these two is the low voltage winding which is near to the core. So near to the core we always place low voltage winding first, and over that low voltage winding high voltage winding is done. Okay, this is same for this limb also. Okay, so inner side is, these two inner is low voltage and upper side is the high voltage winding. Okay, there is a reason behind this. The reason is that for high voltage winding we actually require high insulation level. Okay, and for low voltage winding comparatively low insulation level is required. Okay, so see, since we are connecting this low voltage winding near to the core, so less amount of insulation will be required. Okay, and for high voltage winding, the insulation of each conductors used in low voltage winding will also act as the insulation for this high voltage winding. Okay, so that is why this requirement for high voltage winding insulation will be minimized somehow. Okay, so this way the winding is done. Okay, now come to this cell type construction. So the difference is that here the windings are placed on both the limbs. In cell type constructions you will find that the windings are placed on a single common limb. Okay, and the side limbs there is no winding placed. Okay, so these are two constructions, different constructions, right? In this, you will find the advantage is that the flux which is linking to both the conductors, okay, there is a very less chances of leakage flux, because whatever conductor is linking to the low voltage winding, the same flux will link to the high voltage winding also. But in this case, there may be a certain chances of uh, leakage flux, okay. But since we are placing both the windings on the same limb, here also the chances is minimized, right? So we conventionally learned that uh, you have find that earlier I have drawn the circuit like on this limb only primary winding is there, and on this limb only secondary winding is there. There may be high voltage or low voltage, okay, low voltage winding. So actually practically this is not done, okay. Practically both primary and secondary are wounded on both the limbs, okay. So this is the concept of core type and cell type construction, okay. Now next, on the basis of their purpose, okay, the purpose is either we require to step up the trans voltage or step down. So based on these, we have two types of transformer. One is a step up transformer, one is a step down transformer, okay. So in step up transformer, you see that in the primary side or the input side, the number of turns in the winding is less with respect to the number of turns in the secondary coil, okay. So we know that EMF induced in each turn is equal in both the windings, okay. So as the number of turns increases, the voltage across the terminals will also increase, okay. So here we can clearly see that whatever voltage we apply here, the voltage level at this output side will be more, right, will be more, its magnitude will be more with respect to this one. So this is step up transformer, okay. Now next, step down transformer. See here, the primary coil has more number of turns with respect to the secondary coil. So whatever voltage will be here across this primary winding, the voltage available at the secondary or output terminals will be less than this one. So basically it is stepping down the voltage. So that is why this is called step down transformer, okay. Now on the basis of type of supply, this is single phase transformer, okay. In single phase transformer, you will find there are two windings only, okay. One winding is for input terminal, right, for input, and another winding, from another winding we get output, okay. So only two input terminals are available and two output terminals are available for single phase transformer, okay. So in single phase transformer, we give input as a single phase AC supply, and we also get the output as single phase AC supply, but having voltage level changed, keeping the frequency of input as well as output same, okay. Now, three-phase transformer. See, in three-phase transformer, it is basically we can connect three single-phase transformer to make a single three-phase transformer. Okay. So see here, we will have three windings for primary and three windings for secondary. Okay. These three windings can be connected either in star or in delta. Similarly, these secondary winding may also be connected either in star or in delta. So it depends. So whenever when we will learn this three-phase transformer in great detail, I will tell you how these windings or coils are connected in different ways. Okay. So this is three-phase transformer. Now see, on the basis of their use, okay. So there are two types of transformers. One is power transformer and another is distribution transformer. Now see, this is power transformer. See the picture. The power transformer is a one kind of transformer that is used to transfer electrical energy in any part of the electrical or electronic circuit between the generator and distribution primary circuit. These transformers are used in distribution system to interface step up and step down voltages. Okay, so this is power transformer. Hope you understood, right? Now see this distribution transformer. Okay, what is this distribution transformer? This distribution transformer is also known as pole mounted substation. Okay, so a distribution transformer or service transformer is a transformer that provides the final voltage transformation in the electrical power distribution system, stepping down the voltage used in the distribution lines to the level used by customer. Okay, this is also called service transformer. Okay, so its secondary voltage, that is the output voltage, will be uh, line voltage will be 415 volt, and phase voltage will be near about 230 volt, and primary voltage is normally it is 11 kV, or sometimes it is 33 kV also. Okay, now there is practically no difference between the power transformer and distribution transformer. Both transformers have same basic principles. The only difference is the relationship between maximum efficiency and the load on the transformer. Okay, power transformer is located at the generation end and hence has to transfer whole power that is generated by generating station, and hence is designed in such a way that it gives maximum efficiency at the rated or 100% load. Okay, so in transformer, maximum efficiency is achieved when iron loss is equal to copper loss. This I will derive later on. Okay, for the time being you should understand that maximum efficiency condition is that iron loss should be equal to copper loss. So in power transformer, iron loss is equal to copper loss when it is operating on the full rated load condition. Okay, so that means its core loss should also be high to match that copper loss. Why? Because it is transferring more amount of power, so it will lead to more copper loss. Okay, fine. So to achieve that maximum efficiency, copper core loss will also go up to so that it will be equal to copper loss. Okay, for maximum efficiency. So in power transformer this happens, right? While in distribution transformer, due to unknown distribution load, it is designed in such a way that maximum efficiency occurs at half of the rated load. Okay, meaning that it is designed in such a way that iron loss becomes equal to the copper loss on the half load. Okay, this becomes equal to copper loss on the half load. So this is the difference. Fine, that means in distribution transformer you will find the core loss is less with comparison to the power transformer. Okay, now see instrument transformer. These transformers are basically used for relay and protection circuits. Okay, they are also used for measurement purpose also. So current transformer, in current transformer actually see here in the figure it will be much more clear. This is the symbol for current transformer. Okay, and this is showing the current construction of current transformer. See this line, suppose this is a conductor where high amount of current, that is I1, is flowing, say in the range of 1000 ampere current is flowing through this line. Okay, fine. So we cannot measure this 1000 ampere directly with the help of an ammeter. Fine. So we need to step down this current to a level of 5 to 10 ampere. Okay, so that we can measure this current easily. Okay, so we need a transformer whose secondary number of turns will be more, right? And primary number of turns is actually one turn. See here, this is one turn passing through this, and in the secondary the number of turns is more. So what will happen? Basically, the voltage level will step up, right? And in a single conductor, the voltage level across this conductor is actually very low. Okay, so it will step up the voltage. So basically, stepping up the voltage means stepping down the current level. Why? Because the power in the primary circuit should be equal to power in the secondary circuit. So V into I will be V1 I1 will be equal to V2 I2. So here uh, V1 is less, right? And I1 is more. So in the secondary side, since voltage is stepping up, that is V2 is going up. So to keep this power constant, I2 must go down. Okay, and then we can easily measure this. So this is the concept of current transformer. You will be uh, studying or learning this topic in great detail in the subject electrical measurement and measuring instrument. Okay, now this is potential transformer, PT, or voltage transformer. Here also the same thing happens, but here we actually step down the voltage level. Suppose we need to measure a 33 kV line voltage. Okay, so we cannot directly measure that 33 kV line directly with the help of a voltmeter. So we need to step down this with respect to step down the voltage level from high voltage to low voltage so that we can measure. Okay, so this transformer is used. Here the primary number of turns will be more and secondary will be very less. Okay, so in that ratio it steps down the voltage to a very low voltage level, right? So that we can measure it easily with the help of a voltmeter. Okay, fine. So hope this is clear to you. Okay, if you have any doubt you can ask me in the comment box. I will certainly reply it. Okay, fine. One more important thing is that the power capacity of these transformers CT and PT is very less, right? Why? Because either voltage or current, any one of these parameter is very low. Okay, in this case, primary side, you see the voltage level is very low. In the secondary side, current level is very low. In potential transformer C, in primary side, the current level is very low, and in secondary side, voltage level is low. So you will find that the power which is being transferred is near about in the range of 15 VA. Okay, so it is very less. Okay, because this is used for only for the purpose of protection or measurement, right? This is not used for the purpose of transferring power and connecting some load to this. So that is why the load, right? The load means we may connect some voltmeter, ammeter, or it is directly connected to some relay or switchgear protection devices, right? So they are not called as load, so we call it as burden. Okay, so you will find that for these transformers the load is actually a burden, it's not a load. Okay, fine. Now let us proceed. Now, on the basis of cooling employed, so normally what happens that a transformer gets heated due to its core loss and copper loss in the transformers, right? So it is required to cool the transformer for its normal healthy operation. Okay, so these are the methods which is generally used in power transformers. Okay, so first is this oil natural, air natural. Natural means nothing will be forced, right? So oil is used in transformer tank for two purposes. One is for its cooling purpose, another is for insulation. These are actually insulating oil used in transformers. Okay, so oil will naturally flow. See here in this picture, you can find this is the oil used, right? So this oil will naturally gets heated up, and since it hits, it will go upside, right? And it will flow through these radiators, comes down this arrow, you can see that, and again in radiator it will cool, right? uh, with the help of air, natural, right? And again it will go back to this tank again. This cool oil will gets heated up in the windings, right? Or core, the losses due to the core losses or copper losses, again it will go up, and again, so like this it will move, right? So this is the natural process. Fine. So this is called oil natural. And in the radiator, right, there is a natural flow of air, right? So due to that, it cools itself. So this is called ONAN, oil natural, air natural. And this is when the this is applied when the temperature of the transformer tank or transformer is within certain limit, right? As the temperature of the transformer increases, this second will come into force, that is oil natural, air forced. Oil will be naturally flowing, but this fan will get starts, right? So that it cools quickly. Fine. Again, further, if the temperature rises, oil will also be forced. That means oil forced, air forced. This pump will start, right? Which will forcefully circulate this oil inside the tank through radiator. Okay. So this fan is also on. This pump is also on. So this is called oil forced, air forced, right? And the last is oil forced, water forced. Sometimes in special cases, water is also used for cooling of the oil through water sprinkling. Okay. So this is not very common, but these three are very common. Okay. Hope you understood. Now, different parts of transformer and their function. See here. This is the transformer main tank. Okay. Main tank. Inside this, we have this core, three-phase transformer core, and these are the windings. Hope it is clear, right? And inside this tank we use this insulating oil, and as I told that the purpose of this oil is to insulate these windings from the tank itself, and the second is it is used for cooling of the transformer, right? So this is about transformer main tank. Now you see, these are the actually valves. Fine. And this is radiator. Is used for cooling, right? It is fins like structures. In radiator, the area of cross section of these basically oils is spread, right? So that cooling is uh, easily done. Clear? Fine. Now this is pump. I have already explained. This is fan, cooling fan. Okay. Now see here. This is very important thing. You should understand why it is used, right? This is a conservator tank, right? This is breather used here. This is a alarm circuit, and it is inside the Buchholz relay. What is Buchholz relay? Buchholz relay is a protecting device, right? It is a protecting device. Whenever there is a incipient fault inside the transformer tank, this will first give a alarm to the control room, and even if nobody attend this fault, so it will trip automatically. Okay, so these two facilities are available in this Buchholz relay. You will be taught these Buchholz relay in great detail in power system protection. Okay, for the time being, you should know that this is used for protection of the transformer. This is a gas actuated relay, right? Now this, you see this line, this is normally at 4 degrees Celsius. Okay, this is not showing this 4 degree, but it's slightly upward, going upward always, right? So what will happen, the use application is that when the temperature inside the oil or inside the tank is increases, the oil will expand itself. So if it is a completely uh, sealed one, so what will happen, this there is a chances of blast, right? It may explode, so that there is a path, so that if the expansion happens, it will go up and it will be stored in the conservator tank. And again, if it cools down, so its volume will obviously volume will be decreased, so that what will happen, the oil from this conservator tank which was earlier reserved here, so that will come back to fill up this tank. So this is the use for conservator. Hope it is clear. Okay, now concept of ideal transformer. See, this is very important to learn. Okay, although we know that anything ideal doesn't exist, right? But here ideal transformer concept is very important. After learning this ideal transformer concept, it is very easy to learn the practical transformer. Okay, there will be certain additional losses and all. So in ideal transformer means what is supposed to be ideally, right, in a transformer. See here, an ideal transformer is an imaginary transformer which has no copper loss, right, no winding resistance, that means clear, no iron loss in the core. These are not practical, right? But if it is practically, means if we assume that there is no copper loss, no iron loss in the core, then this will be ideal transformer. The concept is that there is no leakage flux in the transformer. This is another, right? In other words, we can say that an ideal transformer gives output power exactly equal to the input power, which is not possible exactly in case of practical transformer due to certain losses in the transformer. The second is the efficiency of an ideal transformer is 100%. Actually, it is impossible to have such a transformer in practice, but ideal transformer model makes problems easier, as I told you, right? Now, the characteristics of ideal transformer. This is very important from exam point of view, and in Viva also it may be asked, right? Number one, zero winding resistance. It is assumed that resistance of primary as well as secondary winding of an ideal transformer is zero. That is, both the coils are purely inductive in nature. Okay, so resistance zero means no copper loss, because I square R loss is there. So if R is zero, there is no point of I square R loss. Okay, next, infinite permeability of the core. Higher the permeability, lesser the MMF required for flux establishment, right? That means if permeability is high, less magnetizing current is required to magnetize the transformer core. So actually we will see that in ideal transformer, for the flow of flux at no load, okay, no MMF is required. So this is the thing which is only found in ideal transformer. Okay, so this is a concept, as I told you. Now, no leakage flux. So leakage flux is a part of magnetic flux which does not get linked with secondary winding, right? As I told you that the flux should link both the windings, right? But practically what happens, that some flux gets leaked, right? So all the flux doesn't link to both the windings. That is called leakage flux. Due to this, certain voltage drop happens. Okay, we will take all this into consideration while we will deriving for the equivalent circuit of transformer, right? So in an ideal transformer, it is assumed that the entire amount of flux get linked with the secondary winding, that is no leakage flux. Okay, And the last is 100% efficiency. Okay, an ideal transformer does not have any losses like hysteresis loss, eddy current loss, or copper loss, etc. So the output is maximum, and so efficiency is 100%. Okay, so for today, thank you.